This is a recording of IDPass applet smart card, the Java card design. We are looking here at IntelliJ IDE simulation of the applets using the G-card simulation. So we're using this to run the applet, and we're loading the source codes in this IDE. And this is the layout. So this is an IDE in IntelliJ. You can run the applets through this IDE in a simulated J-card sim Java card environment, but we can also run the real physical card through this IDE. So we will step debug in this IDE, pressing F8 and F7, step over and step into step debugging in simulation. But take note that we can also do this exact same step debugging into an actual card by connecting the USB card reader and putting a card into the card reader. You can run the entire thing. So this is not just for simulation, this is also for actual run of the applet using the USB card reader. This time we're just using the simulation for now. This does not cover the installation of the applets, so when running through the actual card using this IDE, a separate step has to be done to flash or to install all the caps, and the cap should be so the caps here that is produced here should be installed into the card, then we can debug this actually. Take note, this IDE setup project does not produce the cap. It can be made to produce it, but I did not take time to do it. We still produce the cap files through the Gradle in the command line in the project. So this will just produce the class files because jcard sim do not need cap, only the class files. So it's still not ideal situation, but this is how it works. So the design of this is the actual Java cards that we know is inside is, for example, the base class is in the tools, and this is the base class. And we can see that we are now deep into the base class, this one, and the derived classes that are three. For example, the auth. This is also a Java card auth. Okay. Now this is the method that this design is patterned. Each of these Java card classes, namely the auth, the data storage, and the sum, have mirror replica into the other side, into the client side, into the off card side, and those replica are inside his folder. As you can see, this is the replica of the auth applet, and the replica is a derived class of the true actual Java card applet. It is a derived class. The data storage is also the same. It is also a derived class, as well as the sum applet. the signed applet. So the traditional way of Java card, as I saw it, is the Java card applets, such as this one, runs inside the physical Java card, and then the outside world, which is the off card, communicates inside the card through APDU, and there is no sense of structure after that. They're just APDU, so the structures are inside the Java card. So the classes, the applet, the data storage, the sum classes are inside the Java card as Java classes, as Java objects. But in the outside, on the other side of the world, in the off card, there's no such classes. They are just APDUs, so they become flattened as a series of APDUs. So that is how I saw in every design available at present. So this design is different because in the other side of the off card, these replicas exist, and operations or APDUs that are sent to the card are marshaled through these mirror classes. So that is the main difference. So now the client side or the off card side has to operate on the mirror replica of the off. So I think this is a better design because the Java card classes have mirror replica on the client side. So the client side is actually programming on the Java card applets because every command invoked on these replica classes are marshaled and forwarded to the other side inside the Java card. Yeah, they are still APDU, but at least at the client side, there is no sense of structure. The client is operating now on an actual Java card, simulated mirror Java card classes. Okay, so there were changes made to make this possible. One of them is to change the in the tools. Um, I think this was not inheritable, but yeah, it was the auth. For example, the auth was, I think this was final before or something like that, and got inherited. So therefore, I cannot design this. So I made some changes so that I can extend from the class. So that's it. But the primary changes of this is that the main benefit of this design is this private member. This used to be private. I changed it to protected so that the derived class can access it. In the actual physical card, this object is instantiated inside a card, inside the Java card, and it is the one that enforces the security. But now in the simulated design, this has been pulled out and exposed into the replica classes. For example, here. And because we are now a derived class, we can hijack some methods. That's the key here. The keyword here is hijack. So we can hijack now the methods. So every time the card changes security status, the replica classes are are the one that are the one is notified about it. So we can control. We have a control in this way because of the inheritance of the classes. And by controlling it, the implementation of the Secure Channel Protocol SCP-02 is now made possible through a dummy implementation outside of the card, which is done by this class SCP-02. This is responsible for the secure channel protocol. Another main principle here is that there are two sides, the off card and the card, and each side has an instance of SCP-02. The way that it works is that SCP-02 is a synchronous security status mirroring. So if the off card thinks that it is in state 1, then the card should also be thinking the same. Okay, since the two sides are disconnected by the APD boundary, this is the connection, the ACP02 object. So if the card thinks that it is in state 2, then the off card should also be in state 2. So they are in synchronous. And at first it was speculative, but later on I was able to prove that this is really the case, as I was able to prove in actual scenario. There was a missynchronization of the card and the off card in the real situation, and it breaks the cryptography. I will not mention that what did happen, and I can prove it. So so that's it. So that's the presence of this object, which is present in of the two sides. You see. So for example, in the auth applet, see. Okay, so I did not instantiate the ACP02 for this applet, but instead there's a dummy here. It's here in this one. Here, ACP02. And for the this is in the dummy ISD or security domain, and the other one is in the off card here. Here. So this is the central key of this design. The ECP02 is the synapse, is the link or the umbilical cord that connects the off card to the dummy ISD card. So this is the dummy ISD card and this is the off card, and these two entities are connected through an umbilical cord, which is handled by this SCP-02 object, which is a security state. I believe that that is correct. That is how it behaves actually in the actual physical card. So now let us debug. The main entry point is in the test in the main, and let us now run step debug. Okay, I made a breakpoint into the one of the lowest data structures, which is the ACP02 keys. It's a good thing to put a breakpoint into the lowest, the most bottom data structure, so that you will uh, you will know what happens every step of the way. So let's just step over this one. Actually, these are just my test cases, so let's just okay. Now we are now on the first test case, Circle CI success test. Let's go inside. Get instance. The off card has to get an instance of itself. So there are two sides here, the card and the off card. Now the off card has to instantiate itself. A lot of things happens when the off card is instantiating. Okay, okay, this is not it. Of course, first, we of course the card simulator and the most fundamental primitives like the channel is created, and for this case we're targeting the simulator. Otherwise, it will be targeting to the physical card. This is very symmetrical. So we instantiated that. The most important part of this is the channel, and the channel is passed here. This is the channel. In the constructor of the off card, the channel is assigned to this variable, and now in the off card side, we are now instantiating the umbilical cord, as I said, the cryptographic umbilical cord of the off card side, the ACP02, and passing the keys. This is the constructor of the ACP02. Okay, so now this AZP structures, AZP02 is in the protocol specification, FF02, FF. This is key setting. E02 identifies it as security channel protocol 2. And now it set the security level to 0, which is no security at first. And the bouncy castle cryptography library. Takes a while to initialize. Okay, done. Um, See, I asserted that there shall be only two ACP02 instance. Yeah, this is just a protection. And then I randomize the preferred keys of the card somehow. Yep, I randomize it. Because cards have different settings. Sometimes they have default keys, sometimes their keys they default to the third key, the fourth key, and so on. I just randomize it. And okay, let's go inside this randomization. Okay, in the Java card, the FF key setting. The FF key setting means the default factory. Okay, every card released has a default key or a factory default key. And when the key setting is FF, it means use that default. For our case, that default key is I think 41, 42, 43, and so on. Those are well knowns. But if the card is changed, so the default key is no longer FF, so it could only be either 1 to index, 1 to 5 or something, which will index to another key, which are triples of encryption, MAC, and DEC. So we randomize that to simulate something. And now here we check whether we are running a simulation or in actual. Here I put a note that I will have to use Martin Paljak's way to discover the card manager without using EID values. He has a method to discover that. Okay, this is the part where I told you a lot of things could happen in instituting just the off card. The off card, because to simulate the actual situation of the other side, because there is no other side, right? We create the dummy ISD applet. Okay, we instantiate the off card. but there's no other side. So that's why we created that. We instantiated the other side, which is the dummy ISD outlet. In the real scenario, we don't have to do this because the other side is a physical card. It exists. Here in simulation, it does not exist. We have to recreate it, and that other side is simulated by this dummy ISD outlet. Install. Okay, we are now in the constructor of the dummy ISD applet. Okay, this install method is static. We are not the one who called this method. This is called by the framework jcard called this method. So somehow when we invoke the install, that there are connections inside the simulator that eventually call this static method according to the applet protocol. So when this is called, it is an opportunity for our class to instantiate. So this is the only place where our applet can instantiate when the static method install is invoked. This is standard stuff, and then we register the class into the registry of the card, the GCard sim. Take note that this is also how it looked like in the real applet. And then we have to return the instance. This is my own invention. I have to retrieve the get instance method and invoke it. See, so we are calling now the get instance to return the instance, such that when the instance is returned here, it can be assigned to a left side variable here, which of course this is empty right now, but in other cases there will be a variable to receive the instance. Um, that was a difficult problem at that time. I'll check if it can be improved, but that's how I did it. Then we select the applet because in the JCard SAM, if the applet installed is not yet selected, so we select it. Take note that the select method now is a method of the off guard. One thing here is I use annotations. That's why the annotations like in here contains the package ID, the applet EID, the instance EID, the name of the cup, the install params and privileges that is associated to a particular applet. So we are in simulation. And take note here that we call the simulator and then we call select applet and we pass the ID bytes of the app of the applet. The ID bytes matches to the ID of the applet that was registered a few seconds ago, which we saw during the trace. So when we invoke the select with applet matching this ID, then that applet that was just installed will be summoned to action. Here, select. So we are not the one who called this. So okay, some part of this call we cannot trace because these are callback functions. So we have to put breakpoints in advance. I know that the select method will be called, so I put the breakpoint ahead. So let's see. This is the dummy ISD applet, and the select method is invoked. And it's now instantiating the other side of the umbilical cord. Okay, what is this? Oh yeah, process. Actually, select call calls the process entry point of an applet. That is not very obvious, but it is the flow. So when selecting an applet, it calls the process actually. There, all of those steps we just instantiated on off card. So in summary, this off card instantiation installs a dummy ISD applet to represent the other side of the off card to as its counterpart. Okay. Now the actual applet, for example, the data storage, as it stands now, this data storage is the replica. So okay, the install method of the replica is invoke. So we hijack the install method, which allowed us to trace inside the real applet. So this is now the real applet. Okay, this is now the actual applet, and we can step debug inside this with precision. Like here, we can virtual card repository and so on, and go inside the this fire code. Register that, get the instance. That's it. And now for the sum applet, the same. The install method is invoke, but not the install method of the real applet, but of the mirror applet, which we forward inside to the actual constructor of the real applet. Okay, so this is now the real applet. See, and we can trace exactly step by step with precision what's happening inside the slots repository create. You can go inside there and so on. So what turned out to be a very difficult to debug Java cards now very easy to debug in this way, all because of the mirroring approach, the replication of or the mirroring of the classes inside the Java card, the outside. So there's a lot going on here which I cannot continue because the recording size is getting big in my hard drive. But a lot of complicated things happens in the initialize update and the external authenticate because the real action occurs here. The real cryptography occurs here wherein the secure channel protocol is initiated between the off card and the dummy ISD applet, the simulated other side. The actual code that 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 that's doing this is also the same actual code when the other side is actual physical card. So, but at least here in the simulation and the debugging, we can be step debug it. What else? And there's also Ethereum wallet testing. This is the JSON, and you have to use the Ganache Docker container before that, what else? One thing, I think I made in the yes in the sign applet. Well, I tried to port the standard Java byte array output stream. I didn't think it was a good idea at the time, but I have to state it here. So byte output stream and the complex Bluetooth data element. Well, I should probably rewrite this to the standard BERTLB because these are well known. But I just tried to. Well, this is also an alternative. What you call this? Type length value encoding could be shorter or longer. I haven't measured which one is shorter or longer, but let's see if this merits to exist, continue to exist, or I'll have to do the BERTLB, which one is shorter. Then I also implemented the short and enumeration. These are missing in Java cards, just scaffolding, even the vector. The implementation of these parts I derived from the open source Java project somewhere in the GitHub. Let's see what I can remember inside. Yeah, so the missing part here that I would really like to have is that this program should be able to install the cap files inside the card. Right now, the installation is done via script, shell script. Um, it would be nice if it can be done also in this program. The installation and the cleanup all managed in a Java program here in this app. That's all.